Assalamu alaikum, myself Maryam Ali. Today I'm going to explain you about the assembly programming language of AVR microcontroller. So basically, as I defined previous in the lab one, what is the AVR microcontroller? Is a chip basically will store a code or logic inside it, and according to this, we perform function of on our IDE board. Further on, what is the assembly language? So assembly language is basically a high level language and low level language, sorry. Assembly language is a low level language, and what is basically a low level language? So a level language is a machine oriented. Low level languages are expressed in terms of machine operations that must be performed to carry out a task. So a writer or a programmer have more difficulty in writing a specific code according to the machine operations. As in a low level language, a code is or a code line is or processor is fixed to use some kind of information or logic. But beside this, there is a high level language which is a user oriented, and it is straightforward for a programmer to convert an algorithm into a code, into a program code. So basically, the difference between a high level language and low level language is that both are the machine language or thing we have to for processor. We can use both assembly language or C coding, which is a high level language, but assembly language is more difficult to write for a programmer by using some specific registers. But in general, if we write a program easily into a algorithm into a code, then we use C language usually. So further, now assembly language here. These assemblers are use some set of instructions here. We use some assembly processes, initializations, variables, registers, and so on. Further, what is the advantage of assembly language? Basically, assembly language is a one step further than the C programming coding. If we put a C program or if we put a high level language into our machines or computers, then it have to convert it into a assembly or low level language to convert it into a machine code. But if we use assembly language, then it already in a low level language, then it is more easily transformed or a quick process to convert it into a machine code. So this is why assembly language is but this assembly language is less used as it is very difficult to write for a programmer or to understand for a programmer, and as fast as their instruction execute, the more difficult or more it take time for a coder or for a programmer to write it. Further on, there is the most good thing is that in assembly language there is no difference between the upper and the lower case. The upper and lower case consider same. Further, the AVR registers. As I told you before, that these coding or thing is done in the form of registers or things are stored in the form of registers, and these registers are of two types. One is the general purpose registers that are 32 R0 to R31, but the other are standard IO registers which are used to perform some different things. So basically we are going to see them. These are the port registers. So the port registers are of three types now. Number one is DDRX, number two is port X, number three is pin X. So the DDRX. DDRX is used to define direction, the port X is used to define the output, and the pin is used to define the to get some input. And these all are of 8-bit registers. So further, DDRX, data direction registers. This data direction register of individual pin port, and it contains of 8-bit port. Now these pins are used if we define one pin or some pin, that pin which is defined 1 is used as output, but that pin which is defined as which is defined as 0, then that pin is going to use as input for the port. Further, if we define a pin 1, then we have to use port X to get some output. But we are using 0, defining 0, then we have to get some pin. That is, we have to get some input here. Further, these are some instruction set here. The instruction sets are simple here, not that difficult on lower level here. The first command is LDI. If we have to provide some information, like we have to store some data into the DDRX now, then we have to say LTI DDRX. DDRX X is basically the port defined here. In our AVR 328, there are D, C, and D. So we have to write like LDI DDRA, and onward we have defining 0 or 1, as it is for the direction. Further, we have the add command. The add command is simple, that we have to use two registers here. Now the registers are RD, the registers are from 0 to 31 here. So we can use any register. Now the next command is LDS. We have to load some data into a register, then we use the LDS. If we use to get some data from the register, we use to SDS. Further, the load IO location. If we have to store some IO input output digital logic into register, then we have to use in. And the further, if we have to jump to any command, that is, we are defining a local here, for example T1 here, and our code is here defined further on. And then we need from this step again, then we're going to provide the jump. In C level language we use while, so basically in here we use the jump command instead of while loop. Further, a store register to IO location is similar task as we have to do LDS and the SDS. Now here, for the input we use in, for the output we use out, and for storing some data LDS, from getting some data STS, and increment INC, for the decrement DEC. It is not written here, but for the decrement it is DEC here, and there we have to do register, define register, and the other register and -1. So this is the decrement in the register. This is the decrement in the register value. Further, these are some nomenclature here which is used. This is not used in basically the code, but this is a syntax thing, right? SReg, this is status register. RD, this is for the register file. RR, source file register. Simple R, and the further so on. This is the carry flag, zero flag, and so on. Further, this is the first thing here. The first task was to store 30 in the register R16 in the binary and display it on the board. After then, add 25 in that value and the result on any port. So basically, we have to store 30 in the R16, and by storing that, we have to display it on the port. But further, we have to do after then they become Hojer, then after then add 25 in the value, show result in any port. So in this value, we have to increment 25, I have to add 25, and then again store it on any port. So this is here. The code is here. R16 is defined output and R17 is also defined output. Further, we store a value in the R16, then we also store a value R17 in some register as we have to add, if we remember. Then for the output R16, this is displayed here, like 30 is displayed. This 30 is right in the binary here, and it is displayed as output AR16. But further we have to add 25 here. So add R16, R16 value is 30, and then R17 value is R17 is 25. So this 25, 30 plus 25, and the first register is here R16. So this value is going to store into the R16. So this is the whole thing. Now I'm going to show you here that how this is working. This here, this port A have, this is the 30 here, and after adding 30 plus 25, this we get 55 here. So now for the second task is that we have to take an input from one port and display it on the other. But the simple code is that we have to get some input, and as I know, for the input we have to define the direction register as 0x00, and to display it we're gonna use 0xFF. So for the R17 it is 0xFF, and for the R16 it is 000. And so we have to input, taking input we use IN R18 pin A, and further for the output we are going to use output B R18, and this process is so ongoing here. So now I'm going to show you that I'm taking a value from this A and storing it into the B here. So this is the predefined things here. Let me clear it first. Now if I'm going to give it 1, this is 1. If I'm going to use this, then this is high, this high, this is high. Everyone is high, then everyone is high. So what is at the input? This is at the output. So this is a simple code here. Further, this is a charging sequence of an LED. So basically, this is a short system that how an LED is blinking one by one. There is 8 bit, so first 0, then 1, then 2, then 3, and so on. So for that, there is a simple code here. So the code is that we are using LDIR16. We define it as the output here. But further, these are the some registers I use here. But this is for our, we can say this is for the delay here. Because if we are not providing a delay in our code, then the things are performed in a jiffy and we don't know what is happening there. So for delay, we use that. This is simple that one is incrementing in the code, and this is how our code is working. So like that, 1, then 2, then 3 going to glow, then 4, then 5, then 6, then 7, and at last then 8 LEDs on. I'm going to show you. This is the here. We're going to see 1, 2, 3, 4, 5, 6, 7, and 8. This is a very fast charging. Okay, further task 4. In this task, take two values from different port, compare them. If port the values are same, show 1100 on third port, and if not equal, then show this. So basically, we have to use three ports here. So we define the A, B, and C here, and from 2 we have to take values, that is input. So we define 2 as 00 for the input, and the third is as output. We will have to define 100, 1100, or this one. So if our R16 is not equal to R17, then this is going to display, otherwise this one. So how this is working here. So the thing is that this is I put we'll find this is 34 and this is 30 here output. So by comparing them, now I'm going to show you by comparing these two, I'm going to get if I'm comparing this VREQ, then we have to get R16. If it is not equal as 34 is not equal to 30, then it's going to display 00110011. But if it is equal to R17, this is a compare resistor CBR16. And this is a BREQ command that break equal to. If equal to, then yes. Okay, go here. But if not equal to, then go to this one. So this is the task here. As if it is as it is not equal, so it's going to show this here. If it is equal, then it's going to show this one. Then these 35, 34, 31 and 30 are going to glow and other are off. At last, the next code is in this task you have to command and write your commands about this program sts jump. So this is basically a code where we have to use some commands. sts I told you the store the register to a specific location. Jump command as a while loop. Move command is basically that we have to store some content into another. Like there is some content in the R17 register equal to 2 and R16 is equal to 5. But now we have to store R17 value in R16 whatever the value is. So for that we are going to use this move command. For the out command, I already told you if we have to get some output, then it is out. Sub, subtraction, increment, plus, plus 1, decrement, negative, or compare resistor here. Or this complement here. That if I have 0011, then the complement is 1100. And similarly for the compare command, there is CP here. So let's go to the code. So to get the more clear view of these commands. So this is here STS. Store direct data space. Register value stored in the address here. So this is some type of address and this is R16. So this R16 value is stored into this some type of address here. Further LDI R17 0FF. This is defined as the output register here. This is out. There's some value is stored into this. Further there's LDI command as you know here. Output command R17 complement R17. So the complement of R17 I have already told you 1100 and complement of this is going to get 0011. Further for the MOV command there is that R18 is now have 5 here. Okay, R18 have 5. Okay. So R17 have 3. But now it's going to have when this going to display then it have 5 value instead of 3 because it is copying R18 value. Further, there's the increment command that R17 is increment from 3 to 4, 4 to 5 and so on. But for the subtraction command there is R17, R18. R17 is 3 here and R18 is 5. Now when this is going to display then the R17 is 2 and R18 is still 5 because whatever the value is going to store into this first register. So when 3 minus 5 2 gets and 2 is stored in the R17 register but R18 remain 5. Further on decrement R19 decrement as you know R19 is here 4 so 4 3 3 to 2 2 to 1 and so on. The jump register here that is going to use here and this is going to for loop never end. Now this is the last task here for this lab today. This is a traffic light system here. So this is a simple traffic light system that I define it. The system is that here three commands are totally used. SPI and CBI. SPI is that one specific bit is going to be high. But if I am going to use CBI, then that specific bit of that specific port is going to be low. And the other commands are call. This call is a function I define here, that is the and delay here. So these are the delay things which I used to make my traffic system stay better. So this is the traffic system here. So this is how it's going to work here. This is here. So the one is green, D is green. Now at A there's a yellow signal that is going to get started. But be ready. The signal is on stop, but be ready. This signal means when both yellow and red are on, that means that a signal is just going to be on. So wait, that now one is yellow that it's going to be on. And this is how this works. In the first loop, there are three loops basically. In my traffic light system, there is a tree basically. When this happen, this is mean this only this signal is working. Right here, the cars are or traffic vehicles are going right. If it is this one, this one here, that is this is red yellow. This means that this is stop. There is no car or vehicle is moving going, but this is going to be set, so be ready. But this is be ready signal that it going to be stop. So this is my traffic signal here. So this is all for today. Thank you.